Hello and welcome. My name is Maxim and I would like to talk to you about the CrazyString Mojo implementation. So, what is a string? Well, for us humans, it's just a text, right? For computers, it's a sequence of bytes. How to encode text in a sequence of bytes? That's an interesting question which we kind of faced for a very long time, and the first approach was the ASCII format, which stands for American Standard Code for Information Interchange from 1963. Problem is, it only reflects the few characters from Latin alphabet, or all the characters of Latin alphabet, but this is it. We can't do anything more with it. So we need more. And here comes the Unicode standard, which has multiple versions. It's reviewed a lot, and latest version is defines almost 150k characters and 169 scripts using various ordinary, literary, academics, and technical contexts. Unicode is ultimately capable of encoding more than 1.1 million characters, which is already a lot, and hopefully it will be enough for the next couple of years. All right, so 1.1 million characters means 4 bytes per character, right? That's kind of like the typical logical theorem. Or is it? Well, thankfully, we have a format called UTF-8, which is actually quite an genius way of representing strings. It represents them asymmetrically. It just say like, okay, it depends on the number you want to represent. If this number will fit in 1 byte, then we store it just in 1. If you need 2 bytes, then in 2, 3 bytes in 3, and 4 bytes in 4, right? So we have this, we can store the values asymmetrically and hopefully just in the space that they need. Also, interesting part of the format is that in the first byte, we actually know how many bytes this code point will occupy, number of bytes. And here is a small Mojo function which can compute this number of bytes given the first byte of an UTF-8 encoded code point. So what we do first, we flip a value, we flip the bits. So here we can see, like, if we had like this bit pattern, we get this. When we had this bit pattern for 2 bytes, we get this pattern. 3 bytes, oops, sorry. 3 bytes, we get this, and 4 bytes, we get this. Then we just say like, okay, let's count the leading zeros. So here we'll get 2, 3, and 4. But the problem here is we get 0. So what we also need to do, we say just okay, and then we just plus this value shifted by 7. So if we shift this by 7, it will be 1. But if we shift those by 7, it will be 0. Right? So this way, we actually have a pretty simple branchless computation to see, like, given the first byte of the code point, how wide is this code point. Okay. Then let's see further. Well, it's a nice story, but what about Mojo and CrazyString, right? Okay, so Mojo represents strings with UTF-8 encoding. It's already good. So if we see a string like this, hello fire exclamation mark, right? Then those are the bytes underneath it, like 103, 101, blah blah blah, etc. All right, how is string data structure defined in Mojo? Well, in current standard library version of Mojo, it is just a wrapper around the list U&A. So we said like, okay, a string is actually for computers just a list of bytes, sequence of bytes, right? So here we just say like, okay, we just have this thing which is just a list of bytes. So yeah, that makes sense in a way. How is the list uint8 defined? Well, it has three properties. It has a length, it has a capacity, and it has a pointer to the actual data, right? So this means that every string, even an empty one, has 24 bytes overhead. The pointer points to the actual sequence of bytes, which represents text in UTF-8 encoding, plus a 0 byte at the end. Why zero termination? Well, zero termination is a relic from the C era, where the length of a string was not explicitly defined, but implicitly through zero termination. Basically, I think actually prepending the string with its length is a Pascal way of doing this. In C, it was just basically you get a pointer to something and to a string, and you say like, okay, read it until you hit a 0, and then you're done. So you always need to compute a little bit in order to get the length of, or maybe a lot actually. Okie dokie. So can we do better? Oh, of course we can. Small string optimization would be a good idea here. So what does it mean? The general idea is to think of the string as a union type, kind of, from, like, I'm talking about union from the C definition. So what we want to do is we want to use the 24 bytes either for the length capacity pointer, how we do it now, or directly encode a small string in it, right? So like if we have this string hello fire, we would encode it directly. So but first I will show you how we do it. But first, quick intro to binary representation of numbers. Well, we have generally 1 byte, 2 byte, 4 byte, and 8 byte numbers, where like basically it's like uint8, we have numbers from 0 to 255. uint16 we have from 0 to 65k. uint32 to 4, what is it, billion, and this is just a huge number. Okay, so pointer and int are 64-bit on 64-bit architecture and 32-bit on 32-bit architecture. That's an important tidbit to know, actually, because then we say like, okay, if we say var length int is equal to 15, then we have 15 followed by 7 zeros, because it's basically 8 bytes, right? But the number is so small that it actually fits in 1 byte. Okay. Or another important tidbit is if we are on big endian machine, then it's flipped. 15 would be first 7 zeros, then 15, which will be important in a few minutes. All right, so let's see. Hello fire exclamation mark looks as following. We have 11 followed by 7 zeros, which is the length of the string in bytes. We have 16, which is the capacity of region where we stored the text. And then we have 8 bytes, which are just pointers, which are defined, which is the value, the address where we can find the actual data, but it's defined at runtime, so I just did some stars, like 8 stars. So, and then somewhere in a different region of memory, we actually have the string. Here we go, followed by what is it, 5 zeros, because our capacity is 16 and the length itself is 11. Okay, but it could be following. We could say hello fire exclamation mark int. We just say 11, which is the number of bytes we occupy, then the bytes followed by just zeros. And those are just our 24 bytes, which we have anyways. All right, how can we do this? Like, what's the magic sauce behind the CrazyString? Oh, well, this is how the struct is defined. In this case, we say like, okay, CrazyString has 3 fields. We have flag byte count, which is uint. We have a capacity, which is a uint. We have a pointer, which is an unsafe pointer to uint. And then we have an alias, which is defined at compile time, where we say inline capacity is the size of self minus 2. Why minus 2? Because like in the first byte, we would like to have a byte length. And in the last byte, we would like to have a 0 termination. So meaning that if we have here, we are on arch 64, it will be 24 minus 2, 22 characters. So a string which is smaller or equal to 22 characters would be stored inline without further allocations. So, okay, so how do we do it? We see here is the initialization function of CrazyString, where we give it a pointer to and we give it a length. So like basically we say, okay, CrazyString, here is a byte sequence, which is a string somewhere, and then just create yourself, right? So, and here we say, okay, if length, this one, is smaller equals self inline capacity, in this case it's 22, as we said, then save buffer as an inline string, right? So what do? We say, okay, self flag byte count is equal to length, self capacity is 0, pointer is also 0, and then we say, okay, the string pointer is unsafe pointer address of self, bit casted to dtype uint, and offsetted by 1. So basically we say like the first byte is the length, is coming from the length, and then the string pointer is actually everything else until then. Okay. Then we have this self-correct bytes count, which I will talk about in a second, and then we just say, okay, now we can actually copy data from pointer into the string pointer. And that's basically it. Okay, well, what is correct bytes count? Well, here it is. As I mentioned before, if we have big endian, then, for example, 11, it would be 0, 0, 0, 0, 0, 7 zeros 11, but we would like to always have 11 on the first position, right? So hence we need to ask if we are on a big endian machine, and this is like a compile time if, so like if you are compiling for little endian, which you probably do in most cases, most of machines currently are little endian, then you would need to do this. But if it happens that you are on big endian machine, then it would be it will automatically byte swap the flag bytes count and store it. So like it will always store in little endian, even if you are in big endian on a big endian machine. All right. So okay, but how does it work for long string now? Right? Like, okay, well, in this case, what we do is basically we say like, okay, if the length was bigger than the inline capacity, then we store flag bytes count is equal not just length, but we push the length 5 bits to the left, right? Meaning that we say that the 5 bits here are zeros. Then the capacity, we round up the capacity to 32, which is the length plus 1 because of the 0 termination. And then we say like a pointer is we are allocating a new region on the heap, which is equal to capacity. We zero it out and we self-correct bytes count, what I explained on the previous slide, and then we say we copy from pointer length to the pointer newly created, right? This is basically it. So in cases where we have lots of, where it's not a small string, we will do a mem copy. Well, we actually do mem copy in both cases, but here we also have an extra memory allocation, and in the previous one we don't have to do it because everything is stored in line. All right, how do we know which type of string we have? Well, in this case, this storing the byte count either shifted or not shifted tells us if we are in small, if we have a inline string or not. So what we have here is a method called is inline string, which gets the flagged byte count. Then if we are on big endian architecture, we need to byte swap it. Important. Then we check, okay, if value is 0, then it's a small string. It's basically 0. It's an empty string, right? And an empty string is small and inline. Otherwise, we just check if the value, if the first 5 bits of the value are bigger than 0. If they are, we have a small string on our hands, inline string. Otherwise, no. Right, and then the question of accessing helper functions. So, for example, we have also here byte length. We don't get it directly from the flag byte counts because, as we know, it is like a mixture. It's not just the value itself. So what we do here, we get the value. Again, we check if we are on big endian. If we are, then byte swap it. Then we say, okay, if we're inline string, then we just take the end and give you just the first 5 bytes, which is the value. Otherwise, we take the value, we shift it back 5 bits, and then you get your byte count, byte length. Right. What about if I want to get the pointer? Also relatively easy actually, right? So we just say like, okay, if we is inline string, then unsafe pointer, address of self, bit casted to uint8, and then give the first offset. So like again, if you have this first offset, we know that in the first byte we have the byte length. If we are in an inline string, so like just give this pointer here, and then it's all good. Otherwise, just give a self pointer, and we're good. Again, very simple. Okay, and here's another function where if we want to get a string out of a CrazyString, also simple, self byte length +1, this is our length, we create a pointer buffer somewhere at with where we allocate the memory we need for, then we do the mem copy, and then we just instantiate the string. Okay. So one more thing regarding small string optimizations. Can we go smaller than 24 bytes? We are smaller on 32-bit arch actually, right? So like if you think about it, as I said, for 32 bits, the int and pointer will be, or uint and pointer will be just 4 bytes each, which makes it 12 byte wide. Meaning that the capacity for small string will be actually 12 minus 2, it's 10. We can only store 10 bytes long strings in line. But we could also be smaller on 64-bit arch. If we know, for example, like, okay, I actually always have very short strings, I would like to actually go smaller in general, then we could just say that, okay, the count can be 4 bytes, the capacity can be 4 bytes, and pointer can be 8 bytes, which in total will be 16, meaning that 14 byte characters will fit in line. On the 32-bit architecture is basically 2 byte, 2 byte, 4 byte, 8 at all, 6 characters in line. So to do this, we need to define the struct a little bit differently. So we need to provide a parameter which we call the dtype, and this dtype also has like a default definition saying like, okay, if it's dtype uint64, if the size of unsafe pointer uint is equals to uint size 64, this is how we basically check if we're on 64-bit architecture. Otherwise, it's dtype uint 32. Everything else stays the same. Because basically here, if we give it a different D type, this size of self will compute the proper size. Anyway. Right, and then when we initialize, we would like to have a constraint saying like, okay, dt should be unsigned integer, and we also want to see that dt must be equal or half of the pointer size. Why is it this way? Making it smaller doesn't make sense because of pointer dictates the alignment. If it's 4 and we give it just 1 byte, this 1 byte will be padded anyways. So overall, the type will be anyways, 16 bytes or 8 byte if we are on 32. Okay, but this is just half of the story. CrazyString is much crazier than that. Oh my god. Okay, what is there else in this data structure? Okay, remember I talked about UTF-8 and how it is asymmetrical, meaning that we said like dependent on the code point value, it will occupy either 1 byte, 2 byte, 3 bytes, or 4 bytes. Okay, so like basically it's asymmetrical, and the problem with that is how does one do indexing on an asymmetrical sequence? I say give me, for example, 23rd or 47 character, and if they are symmetrical, you just say that okay, they occupy just 1 byte or 4 bytes. When 4 bytes multiplied by 47, then you get your 47th element. But if they are asymmetrical, you don't know, right? So like they are kind of like they could be smaller, bigger. It's hard to. And same goes for length as well. We know the length in bytes, this we know, but we don't know how many code points are actually in the string because the representation is asymmetrical. So there are multiple approaches to solve this, and the CPython approach is as following: find the widest code point in the sequence, store the sequence as symmetrical ones based on this the widest code point, right? So like they just saying like, okay, we will scan, we will just restructure, we will widen things which are small into bigger chunks, and then it's kind of like what Amazon does when they deliver packages. They have like package sizes, and they just say like, okay, you have small thing, but we have put it in a big package. We will just put some wrapper around it, and this is how we can actually like do these things efficiently, right? Well, there is another approach done by PyPy implementation where they say, okay, we keep sequences as is, we keep it in the UTF-8, but we'll build up an index for every 32nd element of the sequence. Okay, so we go with PyPy approach optionally, right? But what about the index memory overhead? I talked a lot about saying like, okay, we have this overhead of 24 bytes. This is already huge, even for small strings. We have 24 bytes, which we're kind of wasting. Now I want to add another an index which would widen the string to 32 bytes of overhead, right? Well, we could do this, but we don't do this, right? So like we decide we have a possibility to actually define the struct as following. Here we have our CrazyStruct and CrazyString. Here's the D type. We add this parameter indexed, boom, defaults to true, right? So we build up an index, and but as you can see here, the fields haven't changed, right? We still have just 3 fields with, so it will be 24 at most, 24 at most, and potentially on Arch 32 up to 8 bytes. Right, so like, where do we store the index then? Like, what's this magic again? What's this madness? All right, it's a little bit mad, but like, as I said, it's a CrazyString, right? So, but yeah. Save buffer as a string with buffer allocation. This is our implementation for the bigger strings, right? And here we say like, okay, we add this index size, which we first set to 0. Then we say if we are indexed, then the index size is equal to, we compute the index size given the capacity. If you think about it, like basically the index size is dictated by capacity which we give, and it won't change until we change the capacity. So meaning that the index is actually not a dynamically sized, or like actually like we don't know this index size is we can compute the upper bound. It might be smaller, but we don't care then. We just say that, okay, we expect it to be, it won't be bigger than this. So we have this index size, and then the total buffer size is actually the capacity plus the index size. So in here, the pointer points to, for the pointer, we actually allocate a region for the total buffer size. Not just for the string, but for the index and the string. Okay, we zero it out, then we say like, okay, the string pointer is pointer offset index size, right? So now how we actually structure it, we say like, there is a region on the heap, we say we have a fixed prefix, which will be our index. And then starting from there comes actually our string. So then what we do here, again, we correct the byte counts, and then when we do the mem copy, we copy into a string pointer and from the pointer with a given length. Okay. Then we say if parameter, if the parameter index is set, then we build index. Right. Regarding the index size, how do we compute it? So we say we have the index count from the capacity. This is basically how many entries in the index we will have at most. Plus 1, because we would like to set the first value will be actually the number of code points total. And then we also need to understand like, okay, the index entry byte width. And I will tell you how it's computed here. Basically what we say here is we say index count is quite simple. We have a capacity, we just shift it by 5, or generally is just divide floor by 32. Because we say like we want to store every 32nd code point. Worst case scenario, we have ASCII. Each code point is just 1 byte, meaning that we will have like 1 index per 32 bytes. But it could be actually smaller, but we need to get like the upper boundary for the index. And then index byte width, what we see here is basically we say like, okay, if we generally have just 200 characters, right, we can represent the indexes in 1 byte. If we have 3,000 characters, we can represent indexes in 2 bytes, and so on and so forth, right? So like here, we just say like, okay, index byte width, mean byte width for the provided value, which is just bit width, and then just this is basically just divide by 8 seal. So round it up. Okay, build index. What we do here is we say, well, index byte width, give it to me, given the capacity, and then we say if it's 1, then we store the indexes in uint8. If it's 2, uint16, 4, uint32, otherwise uint64. All right, and then this is a computation where we say like, okay, give me the byte length, and if it's smaller than 32, nothing to do here. Otherwise, char count is 8, text pointer is unsafe pointer. Here we have like a pointer to the index. This is basically index pointer p, and then we say index and p index, and we go through the length and compute the num bytes, define it should be set, where we just say, okay, the character currently character, is it 30 seconds character or not? And then we do this thing. Like, this is a little bit funky. What it does is basically it says like, okay, if we are at 32, then set the index. Otherwise, just keep the value as is. Why we're doing this so weirdly? Well, this is a tight loop, and we would like to prevent branching this way. Right. So it's just computation, no branching at all inside of here, because otherwise you would have branch mispredictions are actually quite costly. This is why we do computation without if else. Right, and then at the end, the P0, so like the P is actually the pointer to the memory, where the first element will be the char count. This will be set here. Meaning that actually, like, if we ask for length in Python in a string, when we ask for length, we're actually interested in the number of code points. Right? Yeah, and this is nice to have like directly computed for the long string. Also, you need to have like the number of code points, because then you actually know like, okay, I have like I don't know, 275 bytes, but I know that I have only, let's say, 59, will it work? 61 characters, meaning that most of the characters are actually 4-byte wide. Right? But we actually we occupied much more space for the index. Doesn't matter. Okay, so this means that for small string and strings smaller than 32, the index and length needs to be computed on the fly, which is a bummer, but it's not that bad, because this is basically small string where we can use SIMDIF for this to actually compute it very efficiently. For longer strings, we prepend the string sequence with an index, where first element is the string length in code points, important, and forward elements are a position of each 32nd character. What is the index space overhead, right? So like basically we say like, okay, there is always this fight between like we have less computations, but we consume more memory, or we consume less memory, but we need more computations. So here is an example. We have 200 byte string, 200 divided by 32 seal, plus 1 is 7, and 7 bytes are approximately 3.5% overhead compared to 2 bytes. So 7 divided by 200 are 3.5. Okay, 30,000 bytes. Here we say divide by 3 plus 1. We multiply it by 2 because we need to store the index entries in 2 bytes, like unit 16, basically, and then we have 938 bytes divided by 30,000. It's approximately 3% as well. If we have 3 million, then we actually have 12.5%, which is a little bit more. And if we would go even further, where we can't represent the indexes in 4-byte, but we would need 8 bytes, then I think it would be even 25%. But in this case, we could actually think about to say like, okay, if we have such huge strings, maybe we shouldn't index every 32nd code point, but maybe every 64 for 128, so that the index size will be smaller, and then we would could actually go again to 3%, with the penalty of computation will be a little bit more expensive. All right, implementation of unsafe pointer becomes a bit more involved, but actually not really. Like as you can see here, this is unsafe pointer method. We say like self is inline string. We just say ourself offset by 1, right? And else we say if we are indexed, then we give you a pointer with offset over index size. We already did this already when we actually computed this, so this should be a known issue. And if we're not indexed, we just give you the pointer itself. How does we get an index for a Unicode code point then? All right, so like this is what we do. We say, okay, we have this index number, and we would like to get you the pointer where this character starts. Right. So what we do here, we get the unsafe pointer into P, and then we say if we're indexed, this is compile time if, right? So like it will not be here. We will go straight to this for loop if we are not indexed. But otherwise, if the index is bigger than 31, we looking for the slot. So like basically, we want to know like which position in the index we are interested in. For this, we just divide it by 32, right? Or just shift by 5. This is the same stuff. And then the index itself, we are interested in the first 5 bytes, basically, right? So then we know the offset by lookup in the index. So we know, okay, the 32nd, like let's say we want 88. So we know we have 32, 64. So we know where the 64th element is, where its offset is, and then the index becomes, what did I say, 72 from 64, 8, right? So here, then we just do like a for loop where we traverse the pointer, check how many bytes we should go further, and then this is where we will land at the end. Okay, and that's basically it, right? So like this is the crazy Mojo thing, CrazyString, right? You can find it on the as a guest. I haven't created a GitHub repository for it yet because like I think it's still an experiment in a way, just to see how it works. Also, like I already spoke with some folks and they asked if we could go not by code points, but actually by grapheme clusters or by user perceived characters, where actually in Unicode, like the idea is that you can have like multiple codes which will be stacked on top of each other, meaning that you have actually like the best example is when you have skin tones. You have like you have one code for like, for example, thumbs up, and then there will be another code which is just the color. But Unicode knows how to combine them, and then you have it like in a different color as Unicode, right? But it's not only important for emojis, it also works for languages where you have like apostrophes and stuff like this, when you need to put stuff on top of each other so that you get a character which people will perceive as one, but internally it could be multiple code points. And it will be possible as well, I would say, what I would like to do in the future is just a little bit more involved to compute an index for this. But generally, it's possible, so we just need to switch, or I would actually parameterize the CrazyString, saying like, okay, it's not just indexed, but we say indexed by code point, by byte, or by grapheme cluster. And then it would be possible. So this is kind of like the outlook, what can be done further with this hello structure. Okay, then this is it from me. Thank you very much for listening and sticking with me at the end. I hope you had a great time, and maybe I'll create other videos where I explain some other experiments which I do with the Mojo programming language. Bye bye.